Okay, so welcome to everybody, and very far also. There are many people everywhere listening to you. So it's a pleasure for me. I will be the president of the session. I'm not only the referee, but also the president, so I will ask many questions. But I will let also some time to our colleagues. I think Nicolas Moes is online.
Good afternoon, everyone.
Okay. And Laura is also online?
Yes. Hi, everyone.
Perfect. Thank you very much. And that's all.
Jean-François is online.
Jean-François. Okay, so you should have come because we have discovered a new restaurant. It's excellent. So, next time. Okay, so we don't lose too much time. The best is that we listen to your talk. We are very eager to have the solution to many fracture mechanics problems. It's your turn.
Thank you for the introduction. My name is Gergely Molnár, and I would like to begin by sincerely thanking the jury for taking the time to review my manuscript and for being here today to participate in my defense. I also want to express my appreciation to everyone in the audience, both here in Lyon and those joining us online. It is truly inspiring to see participants from all over the world, from Japan to Canada, despite the time difference. Your presence means a great deal to me. By the end of this presentation, I hope to convince you that fracture simulation is not as complex as it may seem, and that length scale play a crucial role in understanding failure even in brittle materials. As a teenager, I spent a lot of time playing video games, fascinated by how computer graphics could create such an immersive environment. I always dreamt of describing the real world with mathematical equations. As it turns out, the algorithms used in special effects are not so different from those employed by engineers. The key difference is that in movies, model parameters are tuned to create a specific visual effect, whereas in engineering, these parameters must be determined based on material properties. To start, I will present a relatively complex example, both experimentally and through simulations. This experiment has conducted by my friend Rian Seguir in Nantes during my postdoc years. Here, a projectile approaches from the left and impacts a polymer specimen. As the elastic wave reaches the pre-notch, a new crack initiates at a well-defined angle. The crack then accelerates and branches at a specific point. Interestingly, these features remain consistent across experiments, revealing key fracture characteristics. Remarkably, using just two material parameters, the phase field model is able to quantitatively reproduce the crack's initiation, propagation, and branching. In this talk, I will demonstrate how this is possible through the diffuse crack representation employed by this technique. I will also discuss the additional phenomena we can model using the phase field approach, how to identify the regularization crack length in real materials, and how we can use this length scale to homogenize the toughness of metamaterials, a property traditionally considered non-local. I come from a mechanical engineering background, but my research has taken me across multiple disciplines. I completed my PhD in civil engineering, focusing on the material properties of structural glass. My work spanned multiple length scales. At the atomic scale, I studied the elastic properties of glass. At the mesoscale, I analyzed the impact of manufacturing defects. Finally, at the macroscopic scale, I investigated the total fragmentation or tempered glass using the hybrid discrete and finite element method. My first postdoc took me to Lyon, where I worked on the atomic analysis of plasticity in glasses. Using molecular statics, we identified the macroscopic events responsible for plasticity and developed a microscale inspired yield criterion for silicate glass. Next, in Saint-Étienne, I implemented this yield criterion into a finite element code and calibrated its parameters using microscale experiments. Following this, I moved to Grenoble, where I studied cellulose nanofibrils at 2 different scales, using both atomic simulations and discrete beam-like methods. Realizing that traditional yield criteria fail to account for fracture under tensile loading, I shifted my focus to the phase field model back in Lyon. I then completed my postdoc years in Nantes, working on dynamic fracture in architected materials. After being accepted into the CNRS, I proposed 2 principal research directions: atomic scale techniques for extracting failure properties from small-scale models. This work led to multiple state-funded projects where we successfully identified internal length scales in glasses. Macroscopic fracture simulations. This effort fostered a strong collaboration with Matthijs, particularly with Aurélien Doatran. Through my career, I have worked closely with both academic and industrial partners, notably with the nuclear industry in France and NEG, a glass manufacturing company in Japan. Most recently, I have opened a new research direction in the optimization of architected materials. This work is now advancing through a collaboration with the University of Sherbrooke, focusing on toughness optimization in silicon-based batteries. My work is motivated by a fascinating phenomenon. Notably, when material samples are small, they appear to be much stronger than when they are part of a large macroscopic structure. This phenomenon was popularized in the 1980s by Bažant, particularly in concrete and rock materials. However, the first recorded observation dates back much further, to Leonardo da Vinci, who noted that smaller cable segments seemed stronger than their longer counterparts. Around 150 years later, Galileo Galilei made a similar observation, stating that smaller bones and structural elements tend to be more resistant. However, neither he nor Da Vinci provided a theoretical explanation for this effect. It took another 50 years for Marriott to propose a theory. He suggested that the larger the structure, the higher the probability of finding a large defect. Importantly, he clarified that the intrinsic strength of a material does not decrease, but rather the presence of the defect reduces the observed resistance. Let's explore why defects matter with a simple thought experiment. Consider a structure composed of 2 beams with equal cross-sections. The clamps are assumed to be infinitely rigid under rotation, and we apply a concentrated force on the top. When both columns are intact, the stress is evenly distributed between them. However, if we cut one of the columns, the remaining column must carry twice the load, leading to a 2-fold increase in stress. Now suppose we glue the 2 columns together with an extremely strong adhesive. If we apply the same load, the stress remains identical to the original intact case. However, if we cut the sample at the center, we create an infinite stress peak. As a result, traditional mechanics cannot predict when the structure will fail using a simple stress-based strength criterion. To address this issue, in the 1920s, Arnold Griffith reformulated the conventional approach to material failure. Instead of just comparing stress and strength, he looked at atomic stick interactions. He noted that while the maximum force in an atomic bond can be linked to the strength of the material, the interaction does not simply end at the maximum force, it has a gradual decline. From this, Griffith proposed that forming a new crack surface requires a certain amount of stored energy to be released. He correlated this energy to the integral of the interatomic force. Later, George Irwin provided experimental validation of Griffith's theory. He demonstrated that when a specimen is sufficiently large, it behaves as predicted by Griffith's energy-based criterion. However, when the sample is small, its resistance is better described by stress-based failure criterion. Irwin was also the first to introduce an approximation for the transition length scale. He showed that the simplest material length can be defined using E, Young's modulus, Gc, the toughness proposed by Griffith, and sigma c, the material's tensile strength. Interestingly, while Irwin is widely recognized for developing the stress intensity factor, this particular finding was overlooked for decades. Since Bažant's revival of this concept, the size effect has been experimentally confirmed across a wide range of materials, from silica and ceramics to ice sheets. In the first scientific part of this presentation, I will show how the length scale parameter in the phase field model enriches linear elastic fracture mechanics. I will focus on simple cases where the size effect is most evident. However, we treated phase field simulations as numerical experiments, essentially as black boxes. To better understand the results, we turned to finite fracture mechanics, more precisely the coupled criterion, to explain the observed behavior. This powerful technique helps interpret automatic results produced by the phase field approach. The history of the phase field model dates back to the early 90s. It was van der Waals who first proposed a continuous function to describe an atomic bond, challenging the traditional view that these interactions behave like rigid trusses. He was later awarded a Nobel Prize for his discovery. However, the mathematical foundation of the phase field approach was established in the 1950s by Ginzburg and Landau. They introduced a continuous function to describe discrete phase transitions, arguing that changes between phases should be gradual rather than abrupt. The formulation we use today, however, was developed by Blaise Bourdin, who adopted classical damage mechanics to establish a smooth transition between broken and unbroken materials using a state variable which we will denote as d. Bourdin's approach was based on Griffith's original criterion, which states that a certain amount of energy is required to create a new crack surface. To advance this idea, he used the variation of formulation of Frankfurt and Marigot, which determines the size of the new crack based on an energy minimization principle. However, in their original work, the crack surface gamma was still treated as a discrete quantity. The breakthrough came when Bourdin, Frankfurt and Marigot introduced the crack surface density, utilizing the Ambrosio-Tortorelli function rule to diffuse the crack over a small region, thereby transforming the discrete problem into a volumetric one. However, they ensured that when the internal length scale LC tends to 0, the model recovers the original discrete problem. In a sense, the phase field model allows us to solve fracture mechanic problems using variational methods. One of its major advantages is that it does not require any additional criteria to model mixed mode crack propagation and reproduces experimental observations robustly. In this talk, I will focus on 3 fundamental fracture modes, demonstrating how traditional linear elastic fracture mechanics can be misleading and how different length scales naturally emerge in even the simplest fracture cases. In mode 1 tensile opening, I will show how the initial crack size affects the critical loading. In in-plane shear, I will explain why the crack branches at an angle, depending on the regularization scale, instead of propagating in a self-similar manner as originally assumed by Irwin. Finally, in in-plane shear, I will show how the primary crack breaks into smaller facets, daughter cracks, which then merge to follow the loading direction. In all 3 cases, we will see how regularization enables insights that are not possible using traditional linear elastic fracture mechanics. However, since phase field simulations do not always explain why certain phenomena occur, we will use the coupled criterion to better understand these numerical results. The coupled criterion states that a crack can initiate and propagate only when both stress, strength, and energy-based conditions are satisfied. For example, in mode 1 tensile opening, if the applied load is low a longer crack is required to dissipate the necessary energy to create a new fracture surface. However, the crack does not propagate because the stress remains below the material's strength. As we increase the load, we eventually reach a point where both conditions are simultaneously satisfied. And this defines a finite crack length. By examining critical loading in mode 1, we find that both phase field simulations and the coupled criterion successfully reproduce the experimentally observed size effect. When the initial crack is large, the behavior aligns with Griffith's prediction. However, when the crack is smaller than LC, the failure follows a stress-based criterion. These results allow us to compare LC, the length scale used in phase fields, with the tensile strength used in the coupled criterion. You observe that as LC increases, the tensile strength decreases, a trend that can be perfectly fitted using the homogeneous solution of the phase field method. For shear fracture, contrary to Irwin's assumption, the crack does not propagate in a self-similar manner. Instead, it branches at a well-defined angle, which depends on the ratio between initial crack size and LC. This angle varies between 45 and 73 degrees. 45 degree corresponds to the direction of the principal stresses in shear, while 73 degrees is consistent with experimental observations for very brittle materials with very small process zone. And it aligns with the maximum energy release rate direction. The coupled criterion confirms this behavior with the tensile strength is high. The preferred branching angle is around 70 degrees. However, when sigma c is small, the angle gradually converges to 45 degrees. The third example was inspired by the conference dinner in Madeira. During the dinner, my colleague Aurélien Doitran sacrificed his flan, a gelatinous cube. He cut a notch in the middle of the dessert and applied anti-plane shear using 2 forks. Surprisingly, the fracture pattern mirrored those observed in many brittle materials, forming a hierarchical facet-like structure. Motivated by this, we applied the phase field model to solve the problem, and it successfully reproduced the facet formation seen in PMMA experiments. When summarizing all our correlations, we see the same trend. As LC increases, tensile strength decreases. However, this relation is not a unique single curve, but rather a failure surface. This is confirmed by plotting the length scales derived from the coupled criteria, showing that all distances scale linearly with LC, but differ depending on the loading case. This leads to an important conclusion. LC is not the size of the process zone. While it influences the process zone, locally instabilities depend on the specific fracture case. Finally, as seen in the introduction, the phase field model can accurately capture dynamic fracture patterns. Using only GC and LC, it achieves excellent correspondence with experimental results in terms of initiation angle, branching location, and crack velocity. Interestingly, in both experiments and simulations, crack propagate at a limiting speed of only 60% of Rayleigh wave speed. We attributed this to local stiffness reduction in the process zone. However, when introducing viscoelasticity, this limit is overcome, as seen in polymers seldomly. Ali, a postdoc at the time, correlated this to local stiffness increments, as illustrated in the final slide. We have seen how powerful the phase field model is in capturing various fracture phenomena. Now I would like to shift our focus to an important question: how can we measure different length scales in real materials? We chose glass as our material of interest because it is relatively simple and lacks a macroscopic length scale. Unlike polycrystalline materials, glasses have no grains, grain boundaries or dislocations, making them ideal for modeling at the atomic scale. Silicate glasses consists of randomly distributed atoms forming unique ring structures. This structure was first theorized in the 1930s, but was only recently confirmed using atomic resolution electron spectroscopy. In this study, we use molecular dynamics and molecular statics to investigate the mechanical response of silicate glasses. We employed a simpler pair potential consisting of an exponential and a hyperbolic term, with Coulombic interactions, of course, were handled using long-range solvers or Wolf truncation methods. The glass samples were generated randomly. They were first heated above glass transition temperature and then slowly cooled to form a stable structure. Finally, we verified the atomic structures using experimental measurements to ensure their accuracy. To study their mechanical behavior, we applied quasi-static deformation, meaning time and temperature effects were ignored. Coming from a continuum mechanics background, our goal was to bridge the gap between atomic scale results and macroscopic material properties. To achieve this, we applied a Gaussian convolution technique to coarse grain the discrete atomic data. This technique ensures both mass and energy conservation, allowing us to define quantum-like quantities for atomic scale simulations. Through this approach, we identify the first length scale, the minimum region in which a discrete material can be considered a continuum. For silicate glasses, this length scale was found to be around 8 to 10 angstroms. Although glasses are brittle at the macroscopic scale, they can exhibit plastic deformation if the sample is small enough. For example, here we see a micropillar made of pure silicon dioxide deformed at room temperature. We can see that the micrometer scale glass can behave like Play-Doh. Using molecular dynamics, we tested the material under different loading conditions, varying the pressure state, and identified 3 distinct responses: brittle failure, softening, and plastic deformation. These results allowed us to formulate a densification-dependent yield criterion, which we then calibrated against experimental data, ultimately identifying the yield strength of silica in the range of 5 to 7 gigapascals, a value much higher than those used in standard glass design. At the atomic scale, we can directly observe the microscopic events responsible for plasticity in glasses, known as shear transformation zones. These plastic events involve local shear deformation with a volume change and exhibit an ellipsoidal shape and an exponential decay in strain distribution. This provides us with a second length scale, the size of these plastic zones, which we found to gradually increase up to 7 angstroms as the material transitions from elastic deformation to plastic flow. By summing the strain jumps in these shear transformation zones, we successfully recomputed the macroscopic plastic strain, confirming that these local events are indeed the fundamental carriers of plasticity in silicate glasses. When we increased the sample size along one direction, we observed the formation of shear bands due to the localized softening. For a long time, shear bands were believed to form due to local damage, a reduction in shear strength. However, by measuring local material parameters such as densification, rigidity, and yield strength, we found that shear bands actually increase in density, which in turn increases local rigidity. This contradicts traditional damage mechanics, which would predict a reduction in stiffness. Instead, the true cause of shear band is not damage, but the phase transition that weakens the yield strength. By introducing a gradient term to describe plastic strain, similar to phase field models, we were able to recalculate global energy variations and define a third length scale for glass deformation. Since we are primarily interested in brittle failure, we developed large-scale models to study crack initiation and propagation. One major challenge was identifying the precise location of the crack tip. As shown here, where only 5% of sample's thickness is displayed, it is difficult to determine the exact crack position. To overcome this, we used the phase field model to fit stress, strain, and energy values obtained from the coarse-grained atomic model. This allowed us to identify a diffuse damage zone around the propagating crack. With this information, we were able to distinguish between free and fracture surface energies. In theory, both quantities represent the energy required to create a new surface, but experimentally their value differs significantly. We showed that by subtracting the elastic energy from the coarse-grained potential energy, the free surface energy could be made visible. Examining the global energy balance, we confirmed that this free surface energy contributes only a fraction of the total energy dissipated. By using either the phase field fracture surface or the surface identified through the free surface energy, we obtain toughness values that align well with experimental measurements. This confirms that diffuse damage exists and that it is not plasticity but damage that establishes the correlation between free and fracture surface energies. Now that we have seen the power of phase field models and how to identify regularization length scales for a given material, let's explore how we can use regularization to determine the fracture toughness of a microstructured material. Mechanical metamaterials, particularly lattice structures, are promising alternatives to bulk materials. These structures are lighter, and because of their small scale, their elementary strength is much higher. As a result, they are widely used both in nature and in industrial applications due to the advancement of additive manufacturing. In this presentation, I will show how we can use both Euler-Bernoulli beam models and a phase field approach to analyze the fracture in these structures. We will assume that the beams themselves are flawless and that the junctions do not introduce stress concentrations. The beams fail when the tensile stress exceeds the critical microscopic stress value. This leads us to an important question. If the representative volume element contains all relevant mechanical properties, could we determine its fracture toughness and create a homogeneous phase field model? This phase field model should fail at the same critical load as the lattice and reproduce the crack patterns observed in the microstructure across different loading conditions. Before constructing the model, we need to verify that the unique fracture toughness exists for a beam structure. To do this, we observed crack propagation in the beam model. By measuring the crack length and tracking the change in potential energy, we could define a critical energy release rate. We found that part of initial fluctuation, this value remains constant, independent of the crack length or geometric features. This confirms that indeed the fracture toughness is well defined for lattice structures. To transition to continuum models, we adopted the Kosterrath theory, which introduces an additional degree of freedom and independent rotation at each material point. This allows us to incorporate additional deformation effects beyond the classical Cauchy elasticity, such as extension or shear interactions. In this new model, we introduced curvatures and independent rotations, enabling a more refined description of the deformation and failure. Finally, we defined the Kosterrath energy and introduced two independent damage variables to account for fracture in two perpendicular directions. Because of the underlying microstructure, fracture in these materials involve a directional dependence, leading to four principal combinations of failure modes. Comparing our simulation results to experimental observations, we found excellent correspondence between both models and real-world fracture behavior. In conclusion, this work demonstrates that although regularization length was introduced as a numerical aid, it plays a fundamental role in modeling and understanding complex fracture phenomena. We showed that different length scales arise naturally as a function of geometry and loading, and that these instabilities are not necessarily equal to the length scale used in phase field models. This regularization mechanism is what allows us to recover experimentally observed dynamic crack velocities. Furthermore, we have demonstrated how length scale can be measured in real materials using silica as a case study. Additionally, we showed that damage diffusion allows us to correlate free surface energies with fracture surface energies, addressing a long-standing question in fracture mechanics. Finally, we used regularization to demonstrate that a unique fracture model exists for lattice structures. And finally, we established that the cost-rate description is necessary and sufficient to modeling these materials, both in elasticity and in fracture. Most of the code used in this study is included in a supplementary material of the corresponding paper and is also available on my personal website, along with several tutorials for those interested in further exploring these models. However, there is still much work to be done. For instance, it would be valuable to observe how the process zone develops in real experiments. In the near future, Thomas' work will focus on developing non-singular fits for phase field models. It is well known that the traditional singular Williams series approach overestimates the toughness in simulations. To address this, our approach aims to incorporate a regularization field analytically, providing a more accurate and physically consistent representation. At the atomic scale, with Bažant, we are investigating the weak clean components in naturally inspired ceramic composites and exploring ways to enhance their fracture resistance. Meanwhile, Suhail will integrate our atomic scale observations on silicate glasses to upscale the material model. His work aims to improve our understanding of the indentation resistance of these glasses by employing a sophisticated phase field fracture model for both cracks and shear bending. Finally, at the metamaterial level, Tom's PhD focuses on optimizing the microstructures of silicon-based anodes. While these materials offer a capacity 10 times higher than their graphite counterparts, they are highly prone to fracture under repeated charging and discharging cycles. To address this, colleagues at Sherbrooke University have developed porous metamaterials designed to accommodate the significant volume change. Tom's work focuses on optimizing these material architectures using the phase field model to enhance their durability and performance. However, the ultimate goal is to develop a universal design tool capable of optimizing the toughness of architected materials by effectively trapping crack branches. Achieving this would require developing a robust technique to homogenize the toughness of microstructures, using a continuum-based method to optimize the topology of the envisioned structures, and then finally translating these optimized designs into real beam lattice materials. Finally, I would like to express my deepest gratitude to my mentors for their continuous inspiration, to my PhD students and postdocs for their hard work and dedication, to the jury for their time and interest, to my colleagues, industrial partners, and family for their unwavering support through this journey. And of course, my employer, the CNRS, for giving me the opportunity to dedicate myself fully to research. And last but not least, I would like to thank Aurélien Dautrin, without whom these past 6 years would have been far less enjoyable and productive. His ideas have been and will continue to be fundamental to this work. Like me, he will defend his habilitation at the end of March, so if you found this presentation interesting, I strongly encourage you to attend his as well. Finally, I hope I was able to convey the importance of regularization in understanding failure. Furthermore, if you have any question or would like to explore phase field modeling, please do not hesitate to reach out.